Hello everyone, good afternoon. Now we have to discuss about osmotic pressure. So previously three colligative properties we discussed, and now this is the fourth colligative property, osmotic pressure. What exactly osmosis we have to understand first. Before understanding this osmosis and osmotic pressure, what is a semi-permeable membrane? SPM. Semi-permeable membrane. In that name only you have semi, means small, permeable, permit, membrane like sheet, thin sheet. Semi-permeable membranes. Usually we use semi-permeable membranes. You know, most of the students are bio students. You have egg membrane, onion layer, and potato layer. There's a semi-permeable membranes we can use. Okay, and this osmosis process you have in bio also. So this is the semi-permeable membrane. Means here which allows only solvent molecules but not solute. As I told you in previous, solvent and solute, which has macroparticles, solute has macroparticles, so they are very big. Solvent particles are very small, so they can flow through this semi-permeable membrane. So what exactly semi-permeable membrane means? The particular thin sheet which allow only solvent particles but not solute. Simple example, if you are filtering some tea like that, okay, tea will come out and above you will have a tea powder, correct, like that. So both can be separate, solute as well as solvent. So for that semi-permeable membrane we use which allows only solvent but not solute, that is semi-permeable membrane. So what exactly now osmosis means? Osmosis. Suppose I am considering one particular beaker. In this, exactly at the middle, I am taking Mr. Semi-permeable membrane like this. This is the semi-permeable membrane. Here I am taking only solvent here. Solvent I am taking, or low concentrated solution I am taking here. So here this is the solvent which consists of micro particles, not macro particles, micro. This is solvent. And this middle is SPM. SPM means semi-permeable membrane. Otherwise I will write here. This is the semi-permeable membrane. Here this side, right side, I am considering some particular solution. Here I am taking solution. Generally, a solution consists of solute plus solvent. Here, which will be more concentrated? This is a solution. This is a solvent. This solution consists of both solute plus solvent. Solute plus solvent you have. So solute having macro particles. Macro particles means big particles present. So this solute cannot flow in this way, and moreover this will be more concentrated because here only solvent you have. It's a diluted completely. Solvent consists of micro particles. So now what happened? This solvent will flow from solvent part to solution part. Certainly when solvent is flowing from here, this level will increase like this. This level will increase. Initially I was taken equal volumes, this solvent and solution. Once both was added, the solvent flows from solvent part to solution part. Certainly the level of this particular solution will increase because solvent is increasing. It's becoming slowly low concentrated because solvent is flowing from solvent portion to solution portion. Solution portion. Correct? This particular process is called osmosis. So what is osmosis? If you want, we can define. The flow of solvent from solvent to solution through semi-permeable membrane, or the flow of solvent from low concentrated to high concentrated solution. Low concentrated solution to high concentrated solution. Why sir low to high? Low concentrated means more solvent. High concentrated means somewhat less solvent. Certainly flow of solvent takes place from low concentrated to high concentrated. So that flow of solvent from solvent portion to solution or low concentrated solution to high concentrated solution through semi-permeable membrane is called osmosis. Okay, see what exactly osmosis you have. Now, what is the osmotic pressure? That is our question. Osmotic pressure. Two things we discussed. One is what is a semi-permeable membrane and what is osmosis. If you see, you can understand osmosis happening like this. The solvent flow from solvent to solution. Got it? Otherwise, if it is low concentrated solution and this is high concentrated solution, then solvent flows from low concentrated to high concentrated solution. Then the level of this particular portion will increase because solvent enters in that. This is the flow through semi-permeable membrane like this. Got it? Now let's see the osmotic pressure. Suppose if you are applying some pressure on it by using some piston like this. Suppose here you have a container like this. And I am using some piston, I am using some pressure on it. Actually, this flow will be like this. So apply some pressure. So here if you are using some pressure, some P, this pressure P is equals to pi. Pi means osmotic pressure. When this pressure what you are applying, suppose it became diluted, almost same concentrated, then it will say stop flow. So when you are applying that pressure and this flow pressure, both are equal, then osmosis process will stop, and that pressure is called osmotic pressure. What exactly osmotic pressure? Let's see. The pressure at which stops the flow of solvent from low concentrated to high concentrated. Otherwise, simply osmotic pressure we represent with a pi. The pressure at which, both are equal, the pressure at which that osmosis process stops, that is called osmotic pressure. Got it clear? So at particular pressure, osmosis process will stop. Means it will oppose like this at this particular pressure. Osmosis will stop. That particular pressure is called osmotic pressure. Last and final, I repeat, osmotic pressure means the pressure at which osmosis process will stop, or else the pressure at which the solvent flow will stop from low concentrated to high concentrated solution. or solvent to solution. That is osmotic pressure. See, this osmotic pressure also we can apply for ideal solutions only. So ideal means we have some Boyle's law, Charles' law, Avogadro's law, like that. So here this concept was applied to non-ideal solutions also by Van 't Hoff, that we have discussed later on. But if you consider this solution is ideal, so ideal gas equation, you know, PV is equals to nRT. That is normal pressure exerted by gas. Here the pressure exerted by this particular liquid. So here also we are considering ideal. So ideal condition if you use pi V is equals to nRT, we can use pi V is equal to nRT. Like PV is equals to nRT, here we use pi V is equals to nRT. So what is semi-permeable membrane, what is osmosis, and what is osmotic pressure, we have to understand. Pi is the osmotic pressure and V is the volume of this particular solution, and R is gas constant. Gas constant, don't use 8.314. Here we have to use 0.0821 liter atmosphere per mole Kelvin we have to use. This we have to use R value. Because here we are considering pressure, volume. Pressure is in atm and volume is in liters. Like that we have to use. So R is a universal gas constant, as we know. This we have to use. Only 8.314 we can use, but pressure should be SI unit. That is Newton per meter square. That if you have, then you can use this. 8.314. Okay. Otherwise, if pressure given atm, volume given in liters, then R value we have to take this. Why I am giving you to solve numericals by using this? Pi V is equals to nRT. Got it? So pi V is equals to nRT. I can write as pi is equals to n by V into RT. N by V. This V goes to denominator n by V. N by V, you know, concentration, which we call molarity, capital M. So you can write that pi is equals to molarity into RT. So this is the main important formula for us. Pi is equals to molarity into RT because N by V is number of moles by volume. You know this. So molarity, commonly you can write pi is equals to CRT. Pi is equals to CRT. This is exactly the final relation for osmotic pressure. What exactly C? This molarity. What exactly C? Concentration. Concentration in terms of molarity, not molality, not mole fraction for this osmotic pressure, not any other concentration term. This C is just molarity, capital M. So let's see finally what we have here. So first, what is a semi-permeable membrane and what exactly osmosis process? The flow of solvent, how happens, I was given osmosis process. And next I was given osmotic pressure. Pi V is equals to nRT I was given. Because ideal behavior, because these colligative properties applicable for ideal gases only, ideal solutions only. So ideal relation you can have, ideal gas equation. So for liquids also you can use pi V is equals to nRT. Simple. Why you taken this means, yes, pressure is directly proportional to temperature. Kelly's law. Volume is directly proportional to temperature. Charles' law. Volume is directly proportional to number of moles. Avogadro's law. Those all relations can be applied for ideal solutions. Yes. This was applied by Van 't Hoff and this equation given by Van 't Hoff. scientist. So pi v is equals to nRT is the relation we have to use. So finally you have pi is equals to CRT. So finally we have all four colligative properties. Just have a look at this. What is semi-permeable membrane I said, osmosis I said, and osmotic pressure I said, and what is the relation for osmotic pressure. To calculate osmotic pressure, pi is equals to CRT or pi is equals to molarity into RT. So one more is there, reverse osmosis, that process you know. If this P pressure what you are using, this pressure what you are using, if P is greater than pi, you have one more, that is a reverse osmosis. RO system, we have purification of water, everything, RO. Reverse osmosis, RO. Okay, when reverse osmosis takes place, the pressure applied is greater than this pressure, this flow. Then reverse osmosis takes place. Reverse osmosis means the flow of solvent from high concentrated to low concentrated. When happens, this pressure applied is greater than this particular osmotic pressure. When osmotic pressure, we have to consider this pressure and this flow pressure, both are equal. This flow pressure only we can consider as osmotic pressure, because this pressure only we are applying. This quantity, this flow quantity, pressures both are same. Correct? So reverse osmosis, when we have to consider when the pressure applied is greater than osmotic pressure. If you applied more pressure on it than osmotic pressure, then reverse osmosis takes place. Got it? Now these all we have four colligative properties along with this pi is equals to CRT. All four applicable for ideal solutions but not non-ideal solutions. Just have a look at this. Got it? Now I will write all four colligative properties applicable for ideal solution. Now my question, if non-ideal solution given, how to calculate all these? Means how to calculate relative lowering of vapor pressure, how to calculate the elevation in boiling point, depression in freezing point, all we have to calculate. How? Means I'll tell you one by one. See, let's see all colligative properties. This RLVP is equals to mole fraction of solute is the first one, and the second one is delta TB is equals to TS minus T naught is equals to KB into molarity, and third one is delta TF is equals to T naught minus TS is equals to KF into M, and the fourth one is pi is equals to CRT, where C is molarity. See what I was given? These all four colligative properties applicable only for ideal solutions. All these four colligative properties applicable only for ideal solution. What is the difference between ideal solution and non-ideal solution? Non-ideal solution. Ideal solution. Suppose urea in water or sugar in water. They are ideal solutions. Why they are ideal solutions? Urea, NH2, CONH2, purely covalent, which cannot undergo further dissociation or association. So that is ideal solution. And this sugar in water means C6H12O6. Glucose in water. C12H22O11. That sucrose in water, which is completely covalent, which cannot undergo further association or dissociation. So there is no change in the number of particles. What exactly colligative property? The property which exactly depends on number of particles. So quantity is a matter. If these are the solute particles, there is no change in the number of particles because there is no association and there is no dissociation. So this is ideal solution. Sir, if the solute is not undergoing further association or dissociation, that is clear, ideal solution. Because there is no further association takes place in urea. Urea means everybody know maybe this NH2 C double bond O NH2. So there is no further association and dissociation. So there is no change in number of particles. So there is no change in colligative properties. Because you can observe right side mole fraction of solute here, molality here, concentration, molarity here. All depends on number of moles. All depends on number of particles. So here there is no change in number of particles. So for ideal solutions, these all four colligative properties are applicable. Come to the non-ideal solution. Suppose NaCl dissolved in water. NaCl present in water. How many we taken? Moles. Suppose 1 mole of NaCl was taken. So they are dissociating as Na plus and Cl minus. So 1 mole is converting into 2 moles of ions. Number of particles, what happened? Increasing. So this particular mole fraction or molarity will increase because number of particles will increase. 1 mole you take here, 1 mole of Na plus, 1 mole of Cl minus. Total 2 moles of ions are there. So if number of particles increase, then what happened? Those we have to consider as non-ideal solutions. So here for non-ideal solutions, this particular all four colligative properties we cannot apply directly. This is dissociation actually. In the same way, here association also takes place. Association how, sir? Some molecules will undergo dimerization by hydrogen bond. Here what happened? Number of particles increased during the dissociation. Number of particles will decrease during the association. Suppose 2 moles of acetic acid, if I am considering CH3COOH, how they exist? Do you know? CH3 and you have C double bond O and OH and C OH and double bond O CH3. Actually 2 moles I was written like this, and between these two one hydrogen bond will happen, and between these two one hydrogen bond. So what happened here? Association taken place. Here what happened? 2 moles converted to 1 mole. Number of moles what happened? Number of moles what happened here? Decreased. Here number of moles what happened? Increased. Particles, maybe ions or molecules. Particles. So here ions are there, here no ions, don't ask me. Molecules here, particles means. So very clear, in non-ideal solutions, number of particles may increase, number of particles may decrease. Suppose I am throwing one chalk piece like this. I am just leaving one chalk piece like this. It becomes 2 parts. I am just leaving one book like this or one cloth like this. There is no dissociation. So this is ideal. Chalk piece when I am just leaving like this, that become into 3-4 pieces. So that is a non-ideal solution, undergone dissociation. Got it clearly? So here for non-ideal solutions, colligative properties we cannot apply by taking directly like this. Something required. Got it? What that something I'll tell you now. So first you must have clarity what is ideal solution and what is non-ideal solution. Repeat last and final. The solution which cannot undergo further association or dissociation is ideal. The solution which will undergo dissociation or association is non-ideal solution. Suppose acetic acid dissolved in water or dissolved in some particular solvent themselves undergo some association here. CH3COOH undergone association. 2 moles of acetic acid converted to 1 mole by using hydrogen bond like this. Association, number of particles will decrease. Dissociation, number of particles will increase. During the dissociation or association, the number of particles will change. So these all terms will change. So to apply colligative properties for non-ideal solutions, one fellow was introduced, one important thing. One person, one great person was given one term which we call I, small I. Let's see want of factor I. Want of factor I is the ratio of observed colligative property to theoretical colligative property. Observed by theoretical. Observed means practical. Theoretical means by using formula. What is what exactly? Observed means while doing some experiment in lab. And theoretical means what we calculated by using formula. That is I. Otherwise, colligative property is inversely proportional to molar mass. Because in any concentration term, if you see weight by gram molecular weight by, so molar mass in the denominator means inversely proportional. So you can take I is ulta. Ulta means what? Theoretical molar mass to observed molar mass. This you can take like this. But want of factor I. So this is difficult. Difficult in the sense every day we cannot do practical. We cannot go for lab. So we have another relation, that is number of moles, total number of moles after dissociation or association to the initial moles, that also you can take as want of factor. I repeat, total number of moles after dissociation or association to the initial number of moles. So I you can take total number of moles present after dissociation or association to the initial number of moles present, means initially how much before dissolving in particular solvent. Suppose 1 mole of NaCl means 1 mole you have here. After dissociation you may have different based on its dissociation, degree of dissociation alpha we have in previous, degree of dissociation or association. So I is equals to, you can say it is the ratio of total number of moles after dissociation or association to the initial number of moles. This is want of factor I. Now let's see what exactly want of factor I for dissociation first, with some degree of dissociation alpha. Let's see want of factor for dissociation. Same, we use I. Okay, suppose you are having some AN. This is some particular salt present in particular solvent. Okay, this is converting into Na moles. Suppose it is a weak, it's not dissociating 100% because it's an ideal. Sorry, it is non-ideal. So it is not dissociating 100%. So we have to use degree of dissociation. I told you, alpha is 100%, means that is 100% dissociated. So initially you have 1 mole and here 0 moles. This is initial. So after some time you added this An particular salt to particular solvent. Suppose N alpha moles was dissociated by using alpha. So what are the number of moles after dissociation? After dissociation, this moles will decrease, so it will be 1 minus alpha. This moles was formed previously 0, so N alpha moles will be present. So after dissociation and initially, if you see one more time, initially I am taking 1 mole, means before dissociation, means before dissolved in a particular solvent, 1 mole, because before means there is no dissociation, so 0 moles of Na. After dissociation you have, what happens here, alpha moles if dissociated, undergone dissociated and form N alpha, because 1 mole is giving N moles. So alpha moles will give N alpha moles. Alpha moles will give N alpha moles. How many remains after dissociation? 1 minus alpha remaining. How many formed? N alpha. Therefore what is I? Total number of moles after dissociation to the initial number of moles. Initially how many moles? 1 mole. After dissociation, total moles how many? Total moles means these are not completely dissociated. N alpha only formed. Remaining something is there, 1 minus alpha. So total moles 1 minus alpha plus N alpha. Total moles you are considering divided by 1 because initial number of moles I was given previously. I is equals to total number of moles after dissociation or association to the initial number of moles. So this is I. So what exactly I know? I is equals to 1 minus alpha plus N alpha. So if alpha is taking common, then you will have I is equals to 1 plus alpha into N minus 1. This you have. Alpha is a common, so N you have, it's a plus N and minus 1. Alpha is a common here. So I is equals to 1 plus alpha into N minus 1. Okay, this is exactly I. I is equals to 1 plus alpha into N minus 1. This is for dissociation. I for dissociation. Want of factor I for dissociation. So what exactly alpha here? Degree of dissociation. Suppose alpha was given 40%. Don't take 40 here. 0.4 because degree of dissociation is a percentage. 40% means 40 by 100. Alpha will be 0.4. Got it clearly? So alpha is a degree of dissociation. We use the same in ionic equilibrium. You can check once. Alpha is a degree of dissociation. Suppose 60% was dissociated, they said alpha will be 0.6 because 60 by 100 because percentage given. Correct? So that is alpha. And where N is number of particles. Number of particles after dissociation. Suppose NaCl dissolved in water, 2 moles. So N value will be 2 for NaCl. MgCl2, N value 3 because 1 Mg2 plus 2 Cl minus 1 plus 2, 3. Correct? K4FeCN 6 times. K4FeCN 6 times. This is undissociable part and 4K plus. So how it will dissociate? 4K plus and FeCN 6 times and 4 minus. Consider only ions, not charges. 4K plus and this is a coordination sphere, so which cannot dissociate further. This entire thing will give only one ion. So 6 cyanides, one iron, one, don't count like that. This entirely one ion and this 4K plus. So for this N value is equals to 5 because 4K plus 4 and this entirely single ion. So 4 plus 1, 5. N is equals to 5 we have substituted. Alpha is degree of dissociation. Got it? So I is equals to 1 plus alpha into N minus 1. This is what quantum factor for dissociation. Let's go through this. An is a salt, dissociate as Na moles, initially 1 mole and 0 mole, and alpha moles if undergone dissociated and formed N alpha moles. So after dissociation remaining is 1 minus alpha and formed is N alpha. I is the total moles after dissociation by initial moles. So these total moles initially 1 mole. I is equals to this. Finally I you have. What is alpha and what is N? N is number of particles. Got it? So this is about 1/2 factor for dissociation. Dissociation means number of particles will increase. So what exactly? From this you can have I is equals to 1 plus alpha into N. Suppose alpha only asking. This is I. Alpha asking. Then what you can write? I is equals to 1 plus alpha into N minus 1. Suppose if they are asking degree of dissociation means alpha they are asking to find. So alpha is equals to I minus 1 by N minus 1. This is alpha. This is alpha. Alpha is equals to I minus 1 by N minus 1. Please note this one. This is alpha which we call degree of dissociation. Alpha is equals to I minus 1 by N minus 1. Degree of dissociation is alpha, where N is number of particles, I is 1/2 factor. Why we are calculating 1/2 factor? To apply colligative properties for non-ideal solutions also. Let's go through this. What is I we have for dissociation? For what I am giving this? For dissociation you have I, and this is one example to know number of ions, and this is 1/2 factor, and from 1/2 factor what is alpha you have? Alpha is I minus 1 by N minus 1. Remember this N, please note this. I will come back. N minus 1, N here. Got it? Why I am telling for dissociation is like this, but for association same story, where you have N, there you write 1 by N. That's it. Because for association number of particles what happened? Decrease. Here number of particles what happened? In dissociation increase. So if you understand 1/2 factor for dissociation, 1/2 factor for association, it will be easy. Instead of N, you take 1 by N, that's it. Instead of N, here you take 1 by N, that's it. You will get 1/2 factor for dissociation as well as association. Very clear. Otherwise, let's see how you will have 1/2 factor for association. Please note this and remember this. This. Got it? Just focus 1 minute. Got it? 1 minute I am telling, just pause it and just look at that. Got it? Thank you. And now let's see the 1/2 factor for association. Why 1/2 factor given? I am telling you one more time, otherwise you feel why this fellow is explaining like this. No, 1/2 factor we will use to calculate colligative properties for non-ideal solutions also. Now let's see 1/2 factor for association. Just observe carefully. Suppose XM, this is XM, and converted to some Mn. Sir, why no, you are not writing X here? No, we cannot write because 2 moles is converting to 1 mole in previous acetic acid. 2 moles I was given here. It's converting to 1 mole. So here X I cannot write. 2 moles is converting to 1 mole. So of course in that 1 mole also 2 molecules are there. But number of particles they was associated into 1. 2 become 1. Molecular formula everything same. There is no change. Molecular formula will be same. Molecular weights will be same. But number of particles will be different. Got it? So here Xm converted to Mn. This is example for association. Associated. So what happens now? Initially X moles are there, 0 moles are there. So afterwards what happened? X alpha moles will associated into alpha by n. Sorry, X alpha by n. X alpha moles is undergoing association into X alpha by n. Otherwise, sir, we are confusing this much. In place of that, you can take 1. 1 you take 1 into 0. Okay, X alpha is converted to X alpha by n. Got it clearly? Otherwise, if you take 1, 0, alpha by n. That's it. If you take 2, 0, 2 alpha by n. Depends. Giri 0, Giri alpha by n. Cancel. But initially if you take 1, X will be 1, here will be 1. Because during association, what's happening? Number of particles, what's happening? Increasing or decreasing? Decreasing. So by n we have to take. Got it? So what are the total number of moles after association? Total number of moles after association is equals to X alpha here what are the number of moles after dissociation? After association remaining are X minus X alpha and these are X alpha by n. So these are remaining. These are forming. X alpha moles are associating and X alpha by n are forming here. So what are number of moles after association means? Here total number of moles. Otherwise I will write I directly. I is equals to X minus X alpha plus X alpha by n by X. So what exactly you can write? I is equals to X you take common 1 minus alpha plus alpha by n. So by X. That's why I said if you take 1 also not a problem. X cancelled or not, tell me. So simple thing, for dissociation you will take n alpha. For association by n you have to take alpha by n. For dissociation n alpha. For association alpha by n. Got it clearly? So here you have I is equals to, therefore what exactly I you have here? So 1 plus alpha into 1 by n minus 1. So this is what I. Very important. If you compare both dissociation and association after writing in your notes, you will come to know very clearly. Dissociation means n alpha, association means alpha by n. X, y I written. If I written 1, sir here X moles are there, why you written 1 you will ask me. That's why I am showing with X. Got it? And only the difference here 1 by n we have to take. So what exactly alpha now? Alpha is equals to I minus 1 by n minus 1. This is what alpha. 1 comes here. So I minus 1 alpha is equals to I minus 1 by this term will be in the denominator 1 by n minus 1. Here what exactly? This is for association or dissociation? For association. Here alpha is also degree of association. Just look at that. have a look. Alpha is degree of association. In previous, alpha is degree of dissociation. That's it. Here also, number of moles associated. Okay? So how many was associated? So here same. Alpha is equals to I minus 1 by n minus 1, where n is number of particles associated. Got it? This is about want-of factor I. So want-of factor I we discussed, and want-of factor I for both association as well as dissociation we discussed. And now how to use I for association and dissociation, and how to use this particular I for non-ideal solutions, let's see in our next class.